Right, welcome back everyone. We're going to be dealing with more about 3D shapes today. This is getting quite near to the end of chapter 2. In this video, we'll be taking a look at how we find the volume of some non-prism shapes, meaning the ones that don't have a congruent cross-section as you travel up and down their height. These are ones that have taper to them or some sort of tightening at the top or bottom. Things like this would be pyramids or cones. And there's a different type of non-prism, which we refer to as a sphere, which is like a 3D circle, obviously like a ball. Whether we're dealing with half of it is hemisphere, or the whole thing being a sphere. So that's where we're going today. Let's take a look. Here's the micro concepts here on the list from our chapter introduction. And we're getting quite nearly, as I say, to the end of this this topic in chapter 2. So once again, we're dealing with 3D geometry, solids, surface areas and volumes, and today we're going to be dealing specifically with the non-prisms. These are pyramids, cones, and spheres. Right, so basically what we're doing is we're trying to find a way to compare the height of a pyramid, say for example, with the height of the cuboid or the rectangular solid that could just contain it. Right, so it's just going to fit around it. And there is a consistent ratio. There is a specific proportion of that shape here on the right that is filled up by this shape here on the left. And we're going to learn all about that right now. Now this guy, that's not me, not an Arizona Cardinals fan. He's going to compare, he's going to take in this cylinder and this cone, which have exactly the same height. He's going to fill up the cone with water and dump that into that reservoir that is the cylinder and see how many times it takes to fill it. Now this isn't very precise, but you get a good idea. He's going to be quite careful to fill it right to the top. Pour that in, and now, very sensibly, he's going to mark the side of the cylinder with how high it gets up there. You know, just based on that alone, you might be able to estimate what you think is going to happen. Never mind, we'll watch the video to its end. Not least of which because the music is really cool. And I'd be very surprised if you couldn't guess what's going to happen now. We'll fill this thing up for the third time. Right to the brim. And dump it in. You can see that it just fills the cylinder. So what do we learn from that? What do we learn from that exactly? Well, I think what we learn is that the pyramid is exactly 1/3 the volume of the cuboid that contains it. Now this is what they're saying here in this formula at the bottom, that 1/3 multiplied by AH, where A is the base area of the rectangular solid and H is its height, which matches the height of the pyramid. You take 1/3 of it and you've got an exact match. Okay, so let's continue then. Now, what I've done to try and demonstrate this, I've got a cube and I've made it on a graphing platform, and I'm going to try and fill it up. Well, it's too fast. I'm going to spin it around so you can, with that animation, you can really see the depth of it. And I'm going to highlight one of the faces. I'll take the bottom one here, and I've got a tapered pyramid that goes off to one of the vertices here. I'm going to see how many times I can get that shape to fill up the cube. I can do that. Now we've already seen this with a cylinder, with that guy's video that we just finished there. There's another one there, and then that red one completes the puzzle. So if I'm going to sort of toggle them in and out, you can see that there's the space for the red one there, and there's the blue one underneath it, and there's just that green one space over there to the front left there. There it is. And if I now pull all three and take away the actual initial shape of the box that houses them, you can see that entire space has been filled up. And they're identical pyramids, and so each of them is 1/3 of the volume that contains it. So you've seen this two ways now, once for a cylinder and once for a cuboid, that the pyramid that sits inside it is 1/3 of the volume of the container that would otherwise hold it. And I'll just put them back one more time. There it is. There's your cube again. So that's how that works. So we've covered two very important ideas here. One is that if you take the base area times the height, that is the volume of the entire cuboid or rectangular solid, and take 1/3 of it, you've now got the pyramid that resides inside of it. And that's the base area here. Now the cylinder, as that man showed in his video, is pi r squared, which is the base area, multiplied by its height. Now that becomes volume. But if you take that same formula but just take a third of it, you've got the cone that sits inside it. And here's the important question now. What about spheres? I mean, that's a different type of non-prism. Well, we can do that too. And here's the formula for the volume of a sphere. You take pi times the cube of the radius, and you take 4/3 or 1 1/3 of it. I'm going to go back to another video to see if I can show you why that's true. We're back to this guy. So now there's a sphere of the same height as both the cone and the cylinder. And you still got those graduation marks on the cylinder, those 1/3 marks. I'm going to fill this sphere all the way up. And you can see that it takes a little while to empty this. And there it is. So it's 2/3 of the entire cylinder. But remember that the cone is bigger. 2/3 of the cylinder, which is 1/3 of the cone. That means you could fill up that cone 4 times. So 4 times 1/3 pi r squared h. In this case, h is going to be 4/3 pi r cubed. So there we go. The volume of a sphere is 4/3 pi r cubed. And here's a little bit of a preview of what's coming up next time. The surface area of a sphere, which is just a ball, is 4 times pi r squared. Now that's a very difficult one to prove, and we're not responsible for the proof of these in our course. So I'm going to pass on that. And if anybody is personally interested, I'll guide you through how we know that that's true. But at the end of the day, really, you just need to know that it is true and that you can actually use that formula intelligently. But more on that next time. So we have 2 examples that we're going to take a look at together, and then you can have the rest of the time to work on your own. The Earth is approximately a sphere, not quite a sphere, but very, very nearly, whose diameter is 12,756 kilometers at the equator. Find the volume of the Earth to 3 significant figures, then write your answer in standard form or scientific notation, and then round that answer off to 2 significant figures. Okay, so first things first. The radius is half of the diameter. Be very careful in these questions. If they tell you the diameter, that's not going to work because these formulas are built on the radius, so you actually have to divide it by 2, which I've done. Now the formula for the volume of a sphere is 4/3 pi r cubed, so I take 4/3 pi, replace the r with the 6378 and cube it, and you're going to get your calculator to tell you a walloping big number. Now, since I knew that this was going to be effectively a final answer, I didn't really worry too much about how it was rounded off, so I just said I took that number, it's massive. And this is a perfect reason for why we have standard form or scientific notation, and it's 1.1 because they said into 2 significant figures in part C. That's 1.1 times 10 to the 12th kilometers. That is a lot. Okay, now here's another one. This is a cute little question. I don't know if you can tell from the graphics. This comes from your textbook, and I want you to try this yourself. This reminds me of an IA topic, an internal assessment topic that one of the grade 12s is choosing to do right now. Not exactly this, but it starts this way and then it goes on. A cylindrical can holds 3 tennis balls. Each of the balls, there's diameter given. And then from that you can extrapolate what the dimensions of the can must be. And they want to know how much wasted space is basically inside that can. That means it's filled up with air, but not filled up with tennis ball. If that makes sense. The space is between. Interesting. And the answer is going to be included. So I'd like you to hit pause right now and try that one. And when you're finished, you got an answer, you can hit resume. Okay, here's the answer, and that comes right from our textbook. If you have any questions about that, you can let me know, and we'll make sure you are all set. Okay, here we go. You only have to do these few questions. They're just checking to make sure you can do the volumes from different questions from Chapter 2, and they all come from question number 1 in Section 2H. Okay, that's how I get to work on that. Good luck, everyone.